So I'll be talking about the non-Neumann algebraic semidirect product rigidity. Cyan actually has set the stage really nice for me. And also I'd like to thank Dreambay because he literally gave all the definitions, basic definitions, so that I don't have to go over them again. And I'll be talking a joint work with the Yonat Kifan and Cyan Das. That's we did last year. So yeah, I think by now all of you have seen the definition of group Neumann algebras. So that's basically, and you have seen it in JC stock in this form. Take the left regular representation and then look at the double commutant. Or you can take the weak operator topology closure of this unitary operators. And this is the weak operator topology. I think Dreambay gave a nice definition of this one. So we'll be talking about two one factors. A von Neumann algebra is called a factor if it has trivial center, and an infinite dimensional tracial factor is called a two one factor. So this group von Neumann algebras, they do have a trace. I think you have all seen that in JC stock. So now when it comes to examples, so this theorem is due to Murray and von Neumann from 1936. So they showed that L gamma is a two one factor if and only if every non-trivial element has infinite conjugacy class. So for example, you have free group with 10 generators, and you have this PSLN Z, and then you have this free product. And you can also consider the torsion group, the permutation group with infinite generator, and then you can also take the big product. So the major theme of studying von Neumann algebras are developing rigidity theory in a setting. So what do you mean by rigidity theory? By rigidity theory, you mean that, well, so you have your object gamma, countable discrete group, and you associate the corresponding group von Neumann algebra to it. So it's quite natural to ask, so what sort of property of your group actually remembered by the group von Neumann algebras? So what by properties, we are a bit specific. It's algebraic or geometric properties. So let's look at a bit of history. What sort of rigidity result that we know of, or why do we want to study rigidity theory? So let's look at the non-rigidity theory first. It was a remarkable result of Kohn. If you take two ICC amenable group and then their corresponding group von Neumann algebras are all equal to hyperfinite two one factor. So there's no rigidity here. And if you want concrete example, you can take the root product of Z with Z. You can take the root product of Z2 with Z, and then you can take the symmetry, the permutation group with infinite generating set. And you can notice that in the first group, it does not have any torsion element. In the second group, you have torsion and you have infinite order element. And in the third group, you have only torsion elements. So you can see that the group von Neumann algebra does not remember sort of classical invariants like torsion or rank, even for the generators or anything. And then not only that, this result of Dykema show that you can take any sequence of infinite amenable group, any infinite amenable groups, and you can take their free product. And if you look at their corresponding group von Neumann algebra, they'll all will be isomorphic. So in general, as I said, this group von Neumann algebra does not remember torsion, rank, and generators relations or any classical sort of invariants. So to develop a rigidity theory in von Neumann algebra is a bit challenging. As you can see, so far there is no sort of rigidity that you can see. But still, most of the driving force actually comes from this Kahn's conjecture from 1980. By looking at this property T groups, by proving that its outer automorphism group is countable, and the result of Margulis, Kohn made this conjecture that I think Cyan mentioned this one, that if gamma is an ICC property T group and lambda be any group, if you have the group von Neumann algebra isomorphism, then the groups are isomorphic. That's a bold conjecture. And maybe it has to do something with property T. So far, there is no example known for which this is true. Okay, so, but there's always hope. So let's look at some rigidity result that would, that literally inspired us to look into some sort of specific construction to hope, that we can get some sort of positive result in that direction. The first one is, goes back all the way to Murray and von Neumann. So the group von Neumann algebra of free group with two generator is not isomorphic to the group von Neumann algebra of S infinity times F2. And then MacDuff came, and MacDuff showed that there are uncountably many, in fact, non-isomorphic group factors. Before MacDuff, there were only three known classes of non-isomorphic group factors: LF2, LF2 times S infinity, and LS infinity. And then the result of Collin and Hagorev, they show that if you take uniform lattices in SP N1 and M1 with different N and M, and you get different group von Neumann algebras. And one thing that you can notice that in these two result of Murray and von Neumann and Collin Hagorev, there's something to do with hyperbolicity, because those uniform lattices in SP1, they're hyperbolic, even they have property T. So somehow underlying fact is that they have something to do with the fact that those are hyperbolic and they have property T. Even the next result, Ozawa discovered the solidity for hyperbolic group. And so you can see that in some sense, the generalization of this result of Murray and von Neumann, that F2 is hyperbolic. So, but hyperbolicity has been defined like in pretty late, around 1989 or something. And then this strong solidity result of Ozawa-Pope, the Fn are strongly solid. And then the generalization of this result was due to Ionat-Kirpan and Thomas. They showed that this is for ICC hyperbolic groups. And well, in Kahn's conjecture, we saw that, I mean, he conjectured for every property T ICC group. Now, if you take any random group and you impose the property that the Kahn's conjecture property, and I mean, if any group satisfy that property, you call that group as a W-star superrigid group. So let's look at some of the results that I mentioned. So the first result in this direction was due to Ionat-Pope and Vass. They show that if you take this iterative product, then this group is W-star superigid. So if any mystery group, the corresponding group von Neumann algebras are isomorphic, then the group will have to be the same one. And there are some other example, other read products by Burbeck and Vass. And then there is this example by Yona and Adrian. So in this example, I'd like to draw your attention to the fact that, well, in spite of having all these algebraic conditions that we have in the group, note that this group has some sort of algebraic feature. It is an amalgamated free product of product groups. So somehow, first you have to recover the algebraic feature, and then you somehow conclude that those two groups cannot be any different. I mean, that's somehow the same thing has happened for the first group. So you show that first you show that the group lambda will have to be iterative Ritz product, and then you show that this group cannot be anything other than the group. So what kind of result that you can get, that if you have any isomorphism theta, it will have to be implemented by group isomorphism. And of course, there will be one unitary. You can always see you have to conjugate with the unitary, and then it comes with the cost of character. So from these two examples, we can see that it is really necessary to recover the algebraic feature first, and then we can expect some sort of rigidity if there is at all. And then we would like to call this product rigidity, even though this is just a unique prime decomposition result. So you know that if you have different products of hyperbolic groups, then I mean, this result of Ozawa-Pope shows that you have to have same number of products. It somehow recovers this algebraic feature that this is unique prime factorization. So there is hope that you can recover something. And then, I mean, this result holds for ICC by exact groups, hyperbolic, relative hyperbolic groups, and this rate product groups. And also you can see that this holds for Z2 semidirect SL2Z, even though it does not have property T, but it has relative property T. So, and this is sort of the most intriguing result that, I mean, this is quite different from the previous one, from the Ozawa-Pope one, because if you know that this product group is isomorphic to group von Neumann algebra of any mystery group lambda that you don't know anything about, and then it says that, well, lambda will have to split with the exactly same number of groups, but you cannot say anything about this particular group, except for the fact that their L gamma I power T is isomorphic to L lambda I. All this group von Neumann algebras are isomorphic. And so, okay. So now I'd like to state my our result briefly here, and then we'll get into more details. So, I mean, we observed that property T has something to do with from Kahn's conjecture, and by all this product rigidity and all sorts of W star super rigidity, we thought that there might be some nice place to look into where you have property T. I mean, property T comes quite naturally, and you also have this hyperbolicity structure. And somehow then we try to look for those algebraic properties for those property T groups, and we came up with this result. Suppose you have a gamma, which is of this form, n1 times n2 semidirect q. I'll discuss what these groups are. I think Cyan already discussed a little bit about this groups that rips TQ. This ni semidirect q belongs to this class. And if you know that this group von Neumann algebras are isomorphic, then you get this lambda isomorphic to m1 times n2 tensor and semidirect with H. So you somehow recover this semidirect product feature. And this is not a trivial semidirect product. So you even recover the acting group, Q isomorphic to H. I'll state the theorem precisely in a couple of minutes. So property T, I think you don't need to get into the definition of property T, just a couple of facts that will be really useful. And example is SL NZ for n greater or equal to 3. And property T is preserved under quotient. That's a crucial fact that is like most useful property. Property T, and for the short exact sequence, if you have this kernel and quotient property T, then your original group G has property T. So these, these are basically the property that we will be using later. And the Rips construction, I think Cyan actually explained this Rips construction quite a bit. So what I'll do, I'll just explain it pictorially here. So here, Q is your arbitrary finitely generated group. For simplicity, you can assume that Q to be hyperbolic. And you have H, those two groups in this black color. Those are your input. And then everything else exists. That's what this construction says. That then there exists a short exact sequence where you know that N is a quotient of H, and the short exact sequence splits. And it is hyperbolic relative to Q. So you can see that it is not unique. I mean, you can have lots of different ends even. So I mean, this whole thing, this is not unique. And well, I mean, so if you start with the property T group Q and you start with property hyperbolic group H, then automatically the group G has property T. So I mean that. So here sigma is the outer action of Q onto the outer N. So under all this assumption, we denote this class of groups that N semidirect Q to be Rip TQ. And here is the precise statement of our theorem. Yeah, it looks quite long, but I mean, here you start with the product group Q1 and Q2, where each QI is a ICC by exact weakly amenable property T torsion rationally finite. If you forget about all this property, you can take uniform lattices in SLN1, SPN1. So SPN1, I mean, those are hyperbolic group property T, and it satisfies all these properties. And then if you assume this condition, this Ni semidirect Q in this class Rips TQ, and then you consider this product group with the diagonal action, and you know that its group von Neumann algebra is isomorphic to group von Neumann algebra of any mystery group lambda by this isomorphism theta, then lambda will have to split as a semidirect product. And not only that, you know that this action of H onto this product will have to be this product action, and there will be a character and a group isomorphism from Q to H. So it recovers the acting group from Q to H. But this red color, that's why I put this red color in this core group, we cannot recover this core. What we get that there are star isomorphism theta I from Lni to Lki, but we cannot recover literally. I mean, if you want honest to God rigidity result here, you probably would expect theta I goes from Ni to Ki. But I mean, so that's sort of the partial reconstruction that we have. But it was enough to get this result. So we cannot get technically W star superrigid group here, but we answer other questions. So in a follow-up work, as I mentioned that with Yonat, Cheyenne, and Cyril, we show that the fundamental group of those groups are trivial. And for the second next examples, I would like to define this class. This is the class of all ICC torsion-free residually finite property T groups. And now you just consider this group, this class ST prime, that consists of group G times Q, where your G is in this class, and Q you can take uniform lattices in SPN1. Then these are all non-isomorphic groups. Now if you do the quadratic torsion Gibbs construction with this group that we defined before in here, and then this will be the acting groups. And the corresponding group fundamental algebras will form an infinite family of pairwise non-isomorphic 2-1 factors with property T. In fact, if you take set up all finite index subgroups, this QI, of a fixed property T hyperbolic group, you can take lattices in SPN1, and then this whole family becomes pairwise finite index to each other. If you take any gamma I, that will be finite index to the group gamma. And so since they're finite index, so those are measure equivalent, but their corresponding group fundamental algebras are non-isomorphic. So that gives, that provides basically new counterexample to a question of Dimitri's rectangle that Jeshi mentioned in today's talk in the morning. That those groups are measure equivalent, but their corresponding group fundamental algebras are non-isomorphic. And these are different from the examples that were obtained in this by Kifon and Yona, and Kifon, Santiago, and Sinclair. And this is the definition. This is the definition of measure equivalence. Jeff already gave the definition in his talk. Well, so what we really wanted, as Sean mentioned, that we really wanted to get a family of uncountably many property T non-isomorphic group factors, but we only get countably many here. This would have been uncountable only if this class is uncountable, but it's not known in the literature, but at least we don't know. So we put that as an open problem. The first open problem that we're going to post is the converse to Dimitri's rectangle question, that W star equivalence implies measure equivalence. That question was in the paper of Kifan and Yona, where they solved this. They gave counterexample to the Dimitri's rectangle question. And then the next question is that this class ST is uncountable. And then, it would be really nice to find a property T W superrigid group, which we are working on right now. And then prove or disprove Kahn's conjecture. Well, here the term disprove, it's because we could not recover the core in our main theorem, as we can see. That's why we wrote disprove, but it might be a feature, not a bug, because even in group theory language, you cannot recover the middle group because the construction is not unique. So as a group, even we don't know whether those groups will be isomorphic with different core or not. So that from Rip's construction perspective, we thought that if there is a counterexample, that should be from this side of Rip's construction. And then since I have 1 minute left, so there are other applications. So there was a question by Young and Skalski where they asked to construct maximal von Neumann subalgebras without property T inside a property T von Neumann algebras. So basically, you can take this last theorem that for every rank 1 group, by rank 1 I mean a subgroup of rational numbers with addition, there exists a property T torsion-free group such that every maximal subgroup of Q is isomorphic to Qm. And if you start with such group and look at the corresponding inclusion, and then this is maximal von Neumann subalgebra, and it does not have property T since it's subject to Z. And well, the comments on proof, I think Shine said quite a lot about this. It uses basically deformation rigidity theory and some Den filling of relative hyperbolic groups and hyperbolic embedding in some small cancellation techniques that you can split this relative hyperbolic group as a free product of finite index subgroup of hyperbolic groups, and then you show that and you use malnormality of the group. That's I think that's it. So thank you.